8.4 Conservation of angular momentum. Angular momentum is the product of angular velocity of a body and its moment of inertia about the rotation. So L equals to I omega. L is the angular momentum, I is the moment of inertia, and omega is the angular velocity. Okay, so the formula, we know that I is kgm squared and omega is radian per second. But then radian, we do not write it in the unit. Okay, so kgm squared s minus 1. Okay, this one is quite similar with momentum, where momentum is equals to mv. This is for the linear motion and this is for the angular motion. For angular motion, we also have conservations of angular momentum, meaning that the summation of Li is equals to the summation of L final. Okay, so the angular momentum before and after will have the same magnitude. So let's take a look at the concept of conservations of angular momentum. Okay, so here's a condition where I scatter spins slower when her arms outstretch. So we have seen that I is equals to mr squared when the r is greater. So you can see the r is greater. So I will increase. I increase means that bigger resistance. It's hard to rotate. So that's why the ice skater spins slower. So we know that momentum, initial and final is the same, meaning that the magnitude is constant. So when I greater, omega will become slower. So the next situation is when the ice skater spins faster when her arms folded. Okay, so the ice skater folded her arm, so this will decrease the R. So when R decrease, I decrease. Decreased number of I means that less resistance, so it is easier to rotate. So when I decrease, the omega will increase. The angular velocity is increased, meaning that the ice skater spins faster. Okay, so remember this equation. When I increase, omega decrease. When I decrease, omega increase. Just to make sure that the equation is balanced. Okay, example for that. A figure scatter increases her spin rotation rate from initial rate of 1 revolution per 2 seconds to a final rate 3 revolution per second. Her initial moment of inertia was 4.6 kgm squared. Calculate her final moment of inertia. Okay, so first thing, find the value for the initial angular velocity given that 1 revolution per 2 seconds. So 1 revolution is 2 pi radian per 2 seconds. So this is the first angular velocity. And then for omega 2, 3 revolution per second. So 3 times 2 pi over 1, so 6 pi radian per second. This is the initial moment of inertia. Okay, so we know that the momentum is conserved. Summation of Li is equals to summation of Lf. Okay, so basically we need to find I2. So the I2 is 0.77. The next question is how does she physically accomplish this change? Bagaimana ditukarkan kelajuan dia daripada pi kepada 6 pi? Okay, so awak akan tulis she folds her arms closer to the axis of rotation. So bila dia fold dia punya arm, R dia berkurang. R berkurang, I berkurang. So resistance dia kurang, dia senang untuk rotate lebih laju. Okay, number 2, a merry-go-round of radius 2 meter has a moment of inertia and is rotating 10 revolution per minute. A child of mass 25 kg jumps onto the edge of the merry-go-round. Calculate the new angular velocity of merry-go-round. So the first situation is only the merry-go-round rotating, and then one child jump onto the merry-go-round. So there is a combination of mass over here. Okay, and then we know that the angular momentum is conserved. So the first is only the momentum for the merry-go-round, and second is the combinations of the merry-go-round and the child. So they will move with one velocity. Okay, so just substitute the value and then you will get the final velocity of the merry-go-round with the child.